This video is a very simple introduction to radar technology, briefly covering its history, basic principles, and types of radar systems. It will explain the fundamental components of radar systems and describe how radar detects and measures objects. Finally, it will give examples of the applications of radar. There are various types of radar systems. In this video we will just describe two types: pulse radar and continuous wave radar. Radar stands for radio detection and ranging. Radar dates back to the early 20th century. Initially it was developed for military use, primarily for detecting aircraft and ships. Over the decades, radar has evolved significantly, with improvements in technology leading to diverse applications in civilian sectors as well. Radar systems transmit radio waves towards a target. They then analyze the reflected signals, which enables them to identify the presence, distance, and speed of objects. There are various types of radar systems. In this video we will just describe two types: pulse radar and continuous wave radar. Pulse radar transmits bursts of radio waves to detect objects and measure distances, commonly used in air traffic control and military systems. Continuous wave radar emits a continuous signal, allowing for precise speed measurements of moving objects, often used in police speed detection. Now follows a simplified explanation of how pulse radar works. This shows the block diagram for a pulse radar. The transmitter is a high-power generator of pulses of microwave energy. For example, a typical airfield radar, like an airport surveillance radar, ASR, usually operates with a peak power in the range of several hundred kilowatts and a pulse width around 1 microsecond. However, specific values can vary depending on the radar model and desired performance characteristics like detection range and resolution. The microwave frequency depends on the radar application, but an airport radar will operate at between 2.7 and 2.9 GHz. The transmitter is connected to a duplexer. This is an electronic device that allows bidirectional communication over a single path. It isolates the receiver from the transmitter while permitting them to share a common antenna. The duplexer is then connected to an antenna. The antenna is directional, so it transmits the radar signal in a narrow beam and usually rotates so that the transmitted radio signal scans over an area. The radio signal is reflected off any objects that are within the transmitted beam, and a portion of the reflected energy returns to the receive antenna. The reflected signal is passed back to the duplexer, and the received signal is passed to the receiver. The received microwave signal is amplified and the pulses are then passed to the processor. The processor measures the time difference between the transmitted and received pulses, together with the size of the received pulses. The processor is then connected to the display, which shows the direction of the received beam as the antenna rotates and shows the distance to objects and their relative sizes. The transmitted waves travel towards the objects being measured. They then bounce off the objects, for example aircraft, ships, rain, etc. And the reflected waves return to the antenna. The radio waves travel at the speed of light, and the processor measures how long it took between the pulses being transmitted and received. The distance between the object and the antenna is thus the speed of light, 300 million meters per second, multiplied by the time difference between the transmitted and received pulses divided by 2, since the radio wave traveled to the target and back again. The detection range of a radar system is primarily a function of three factors: the antenna, the transmitted power, The receiver sensitivity. These will now be explained. The power radiated by the antenna will obey the inverse square law. If you have an antenna that radiates uniformly in all directions and a transmitter with a power P, the power density, the power per unit area, at a distance r, from the antenna, will be PD equals P, divided by 4 pi r squared. So, at a range of 2r, the power density will be 1/4 of that at a distance r. At a range of 3r, the power density will be 1/9 of that at a distance r. The purpose of the antenna is to transmit radio waves in a particular direction and to collect the reflected waves from the target for passing to the radar receiver. The concentration of the transmitted power in a particular direction produces an antenna beam. Antennas can be designed to produce different shapes of beam, but in this example, it is a simple cone shape. The ratio of the concentration of power into a single beam when compared to an antenna that radiates in all directions is called the antenna gain, G. For a directional antenna, the power density will be the transmitter power P, multiplied by the antenna gain G, divided by 4 pi r squared. When the transmitted pulse reaches the target, the amount of power reflected back to the antenna will depend upon what is called the radar target cross-section, sigma. This has the units of area, for example, meters squared. So the radar cross-section is the total power reflected back by the target in a particular direction divided by the incident power density. The reflected power received at the antenna is then Pg sigma divided by 4 pi r squared. The power density received from the target back at the transmitting antenna is Pg sigma divided by 4 pi r squared squared. If the area of the antenna capturing the received energy is called A, then the power of the reflected signal received by the antenna is Pga sigma divided by 4 pi r squared squared, or Pga sigma divided by 4 pi squared times r to the power 4. This shows that the received power declines as the fourth power of the range, which means that the received power from distant targets is relatively very small. The radar receiver detects, amplifies, and processes the target return signal. There will always be some receiver noise. This is unwanted energy that interferes with the ability of the receiver to detect the desired signal. It can originate from within the receiver, internal noise, or enter through the antenna, external noise. The diagram here shows an example of the amplitude of the signals outputted by the receiver as a function of time. This line shows the mean or average level of the noise. A threshold level is set in the receiver processor to result in an acceptable level of false alarms, i.e., meaning threshold crossings due to noise. Here are 2 false alarms due to noise. The threshold is set for an acceptable level of false alarms, for example 5 per minute. Setting of the threshold is a trade-off between the false alarm rate and the detection capability. The output from the processor is sent to the display for the radar operator. The most common type of display is a plan position indicator, PPI. The plan position indicator represents the radar antenna in the center of the display, with the distance from it drawn as concentric circles. As the radar antenna rotates, a radial trace on the PPI sweeps in unison with it about the center point. Targets can be seen as a blob on the screen and the range measured. Continuous wave radar, CW radar, is a type of radar system where a continuous wave radio signal is transmitted and then received from any reflecting objects. An example of this is the police speed gun, which uses a CW radar to detect the speeds of cars. The police speed gun transmits a continuous wave signal which is then reflected from the target. The frequencies of the transmitted and received signals are then compared. If the target is not moving, there will be no difference in the frequencies. If the target is moving toward or away from the gun, the frequency of the reflected radio waves when they come back is different from the transmitted waves. This is due to the Doppler effect. When the object is approaching the radar, the frequency of the return waves is higher than the transmitted waves. When the object is moving away, the frequency is lower. From that difference, the radar speed gun can calculate the speed of the object from which the waves have been reflected. This speed is given by the following equation. Speed equals c times delta f divided by 2f, where c is the speed of light, f is the emitted frequency of the radio waves, and delta f is the difference in frequency between the radio waves that are emitted and those received back by the gun. Another type of continuous wave radar is frequency-modulated continuous wave, FMCW, radar. Whilst CW radar uses a constant frequency signal to detect targets which move, if the continuous signal is swept in frequency, the radar also becomes able to detect moving and stationary targets. This can lead to a very simple yet capable radar and is the technique used by automotive radars for adaptive cruise control and blind spot warning. Radar has a wide range of applications across various fields, from military and defense to civilian uses like weather monitoring and navigation. Radar is extensively used in military applications for surveillance, target acquisition, and missile guidance. Meteorological radar systems are essential for weather monitoring, enabling accurate forecasting and tracking of weather conditions. There is a network of radar stations across the world scanning the skies and producing images showing rain, snow, and thunderstorms, helping to forecast the weather. Radar systems are vital for aviation and maritime navigation, enhancing safety by providing real-time tracking of aircraft and vessels. Radar is a critical tool with a rich history and a bright future. Its principles and applications are diverse, making it an essential component in various fields, and ongoing developments promise to further enhance its capabilities. To see examples of radar technology developed by Pi in Cambridge during the Second World War, please visit the Pi exhibition at Cambridge Museum of Technology.